Okay, it should be going now.
Hey,
Yep. You have to say got it. Luca, sorry for all the delays.
Oh, no worries. Next time I'll come in person.
Yeah, we had a local power outage over the whole region yesterday, and a lot of things got messed up.
Oh,
yeah, that's playing the power outage and
It's definitely power outage.
Yeah. Thank you. And it's our great pleasure to have Luca Delacretaz virtually visiting us to give us a talk on his latest development on nonlinear bosonization of Fermi liquids. So just a quick introduction. As you can see, Luca is from Chicago. He's currently a postdoc in the Kanoff Center of Theoretical Physics. Before he joined Europe Chicago, he was a student of Sean Harnell's at Stanford, so we overlapped for a period of time. And yeah, I'm really looking forward to his talk. Welcome, Luca.
Okay, yeah, thanks everyone. Thanks, Charming, for the introduction, and thanks for the invitation. It's nice to see a few familiar faces, although it's just a few pixels on my screen. So if you, and the sound is also a little bit approximate, so maybe if, I might ask you to repeat if you have any questions. But I would be really happy to have a lot of questions, so let's keep it very informal. So feel free to interrupt. So I'll be talking about this recent paper, which was done with these collaborators. So Xian and Umang are two students at the University of Chicago, and it was also done with Sun. And so it's on basically our work. One of the results of our work is to develop a new effective field theory for Fermi liquids. So Fermi liquids and just kind of fermions in general at finite density, I think are very cool, state of matter. And one of the reasons that makes it very both interesting and difficult to study is that it's extremely gapless. Especially if you compare it to kind of the more conventional quantum field theories and quantum many-body systems one sees in particle physics, where gapless excitations are usually, in the origin and momentum space. Fermi liquids have, basically fermions at finite density. You populate all these states, and your gapless excitations live in this whole locus of at the Fermi surface. So there's really a lot of kind of gapless stuff going on. In some sense, there's an infinite amount of gapless fields. And you can think of these gapless excitations kind of as wobbles or modulations of the Fermi surface. Now, in this, when you have a Fermi surface, there's an important dimensionful quantity, which is the Fermi wave vector, Kf. And so you might ask, is there an effective description for this system, for this type of systems at distances very long compared to 1 over Kf? And the answer is yes. So if you imagine you have a very big system, you can separate it into a bunch of smaller subsystems that are still much bigger than 1 over Kf. And so in each of these, you can kind of play the same game of populating your momentum states and build a Fermi surface. So you can have a kind of Fermi surface at every point in space. So this is really a kind of inherently semi-classical picture. There's both space and momentum space, but it's allowed because we have this large dimensionful parameter. And now the Fermi surface, the kind of state can depend on space. So for example, there can be more electrons going to the right over here, more electrons going to the left over here. And what's inevitably going to happen in this kind of state if by time evolve is that they're going to flow to this box in the middle, and the density is going to increase here. So we see that there's some kind of continuity relation going on. And this continuity relation is just the collisionless Boltzmann equation, this kinetic equation for the distribution function. So here, this is kind of how free fermions at finite density work. But one of the major achievements of the 20th century was Landau's Fermi liquid theory, which was the realization that interacting fermions are almost described by the same equation. The degree of freedom is still basically unchanged. It's still the distribution function. And there are nonlinear corrections to this equation that are parameterized by Landau parameters, but otherwise qualitatively the physics is very similar, and it's very robust. It's very stable. Fermi liquid theory now is an extremely successful and fairly well understood theory. Probably the textbook application is helium-3. It has a number of predictions that can be tested. One is the fact that the specific heat is linear in temperature. This is another, again, a way of seeing how gapless it is. So if you had a kind of system of, like a particle physics type system, the specific heat would go like temperature to the spatial dimension. Whereas here it goes like temperature, which at very small temperature is much larger. And it's really telling us that there's a lot of stuff ready to be excited. There are other predictions of Landau's Fermi liquid theory. There are collective excitations that can be observed. You can actually measure these Landau parameters, these corrections to the free Fermi gas. We'll see how we can think of these Landau parameters as Wilsonian coefficients of an effective field theory. And you can also, also there are predictions on transport out of equilibrium physics and so on that are very well borne out. But Fermi liquids don't just apply to helium-3. The reason we care about them a lot in condensed matter physics is that they describe essentially all metals. So there, one can even visualize the Fermi surface. And the symmetries are a little different, but still qualitatively, this whole theory of Fermi liquids applies and controls a lot of observables in these systems. Even beyond condensed matter physics, there's a lot of applications. The idea is so general. You just need fermions at finite density that it applies in many areas of physics. Part of the QCD phase diagram is expected to be in a Fermi liquid phase. And even in astrophysics, things like neutron stars are expected to be, well, are Fermi liquids. So there's a lot of reasons to care about Fermi liquids, but there are also some reasons to want to go beyond Fermi liquid theory, both from experiments and theory. So on the experimental side, there are a number of systems that seem to go beyond the Fermi liquid paradigm to have physics that's not well described by Fermi liquids, even though there's still a kind of remnant of the Fermi surface. So one example is the strange metallic phase of high temperature superconductors, or quantum Hall systems that have filling is another example. But there are also theory reasons to want to go beyond Fermi liquids because basically just because it's possible. So we know that Fermi liquids have instabilities if you couple them to gapless boson towards, so what this usually does is that it triggers a renormalization group flow to a new fixed point, which can have non-trivial scaling and can be very interesting. So those are generally called non-Fermi liquid fixed points. And so the idea that these two might be related, so it may or may not be correct that non-Fermi liquid is the right way to approach, for example, strange metals, but just to say that there are many reasons to want to go beyond Fermi liquid. In fact, one of the early advocates of going beyond Fermi liquid theory was Phil Anderson, in particular in the context of high temperature superconductors. But even in this context, he also advised us to know the enemy being Fermi liquid theory. And I think there's a very pragmatic reason to want to know the enemy very well, because even if you're interested in non-Fermi liquid fixed points, essentially all these construction of non-Fermi liquid fixed points start from a kind of UV, which has a Fermi liquid coupled to a gapless boson. And I'd like to argue that we actually don't know this starting point well enough to do this, and this has led to challenges in understanding non-Fermi liquid fixed points. So from my perspective, the right tool would be an effective field theory of Fermi liquids, so this object here. So what do I mean by effective field theory? What I mean is a microscopic insouciant description of a system based on general principles. And an example that appears in a lot of kind of subfields of physics is when you have spontaneous symmetry breaking. There, just the fact that you spontaneously break a symmetry kind of tells you from very general principles that you will have a weakly coupled degree of freedom, a Goldstone boson, one or several Goldstone bosons, whose kind of dynamics is completely fixed by symmetry. And so examples include spin waves in ferromagnets or pions in quantum chromodynamics. And basically, symmetries alone tell you that to leading order, these systems are described by something like a nonlinear sigma model, where the degree of freedom lives in some kind of quotient space. These effective field theories also have often interesting terms, like Wess-Zumino-Witten type terms, here related to the Berry phase of ferromagnets, or this is the Wess-Zumino-Witten term in the Pi-Lagrangian, whose coefficients are sometimes related to anomalies and can be quantized. But more generally, the spirit of effective field theory is to write down every possible term that's allowed by symmetries. usually in a gradient expansion. So in an expansion in gradients and also in fluctuations. And here I didn't write this down, but all of these terms come with unknown coefficients that, Wilsonian coefficients that aren't universal, that depend on the microscopics. And that's why I called it microscopics insouciant rather than indifferent. So it does depend on the microscopics in a way, but in a very mild way. Basically, we can parameterize our ignorance of the microscopics only in a few unknown coefficients. And the power of effective field theory is that it can give a lot of answers in terms of just a few unknown numbers. So we'd like to do this for Fermi liquids. So there has been an attempt at recasting Fermi liquid theory in an effective field theory in this beautiful work in the 90s. And the idea roughly was to just say, okay, we have fermions that have some dispersion relation. And then one writes down the most general interaction between these fermions in momentum space. And what this work has kind of really nicely shown is in a modern, Wilsonian RG framework, why out of all these possible interactions, the only ones you really have to care about are the Landau interactions, Landau parameters, and the BCS couplings, because those are the only ones that are marginal under renormalization, whereas everything else is irrelevant. So that comes out very, very nicely from this approach. But there's several major limitations to this approach. One is that it's formulated in momentum space, which is a bit unusual for an effective field theory. But one much more kind of pragmatic one is that if you actually take this action and start doing perturbation theory or whatever, you'll find that there are many subtle cancellations in perturbation theory, particularly in fermion loops. So I'll give some examples in a bit. And these cancellations make things pretty complicated. It's hard to even guess how a particular correlation function will scale because there can be many cancellations. So there is an alternative to this approach, which was also developed around the same time, called bosonization. I'll say a few words about how this alternative is pretty good at avoiding these cancellations. But in this bosonization approach, it wasn't really known what the rules of the game were. It wasn't really formulated in an effective field theory language, in particular how to systematize this approach. And so this is what our work will do. So our strategy will be to write down an effective field theory directly for the shape of the Fermi surface, or this kind of distribution function. And what we'll see is that, so this is going to give a kind of fully nonlinear theory that will, whose nonlinearities are kind of fixed by geometry. And upon linearization, we will recover these kind of older bosonization works, but it will tell us how to parameterize all possible interactions, so all possible corrections to this work. So the plan of the talk is first I'd like to spend some time advocating for bosonization, for this kind of bosonic approach to Fermi liquids. Then I'll explain how we get our nonlinear effective field theory from a mathematical framework called coadjoint orbits. And finally, I'll show you how we can use it to do both, to recover old results, but also to go beyond and do new things. But maybe before starting, I'll pause for questions.
So the higher dimensional bosonization had issues because of like interpatch, right? The curvature, not being able to handle the curvature.
Yes.
So is that what you were able to overcome by taking this, different angular momentum channel, like as a ground zero from the beginning?
Exactly. Yeah. So yeah, we basically solved this problem of the Fermi surface curvature and how patches couple to each other.
I see.
Yeah. So as we'll see in a kind of linear, the first approximation, they don't couple, but the nonlinear terms make them couple. I
see. Very cool. Wow. Look forward to it.
Okay.
Sounds magical, but also still plausible because it makes sense. Yeah.
Yeah. No, it should have, something like this should have existed. Any other questions? Okay, so let's start just with bosonization. And here I'd like to just kind of tell you or remind you how it works in one dimension where it's very well understood. Also to kind of, show you the magic of bosonization and convince you that it's useful, even in this kind of simplest case. So we're going to look at the simplest case of a free Dirac fermion, which can be shown to be dual to a free relativistic scalar. And even in this case, so there both sides are free. It might seem like, okay, why would one description be better than the other? But we'll see that there's some advantage to the bosonic description already. So both theory has conservation of charge. It has a U1 symmetry. The density operator in the fermion side is a fermion bilinear, whereas on the boson side, it's linear in the boson field in phi. And this will lead to some simplifications. So now let's say we want to compute linear response, 2-point function of the density. On the fermion side, you would have to compute this fermion loop. Whereas on the boson side, it's just a tree-level diagram, right? And it's so simple that we can basically evaluate it live. So there's a boson propagator, and then there is a factor of q squared coming from the relation between the density and the boson. So done. Okay. Already here you see that there's a small computational advantage in this bosonic description, but this becomes much more dramatic when you want to compute higher point functions. So if you want to compute a connected endpoint function of densities, on the fermion side, you'd have to compute this fermion loop with n insertions, and you'd have to symmetrize over these insertions. So account for all possible diagrams. And even for free fermions, this can be a tough calculation. Whereas on the boson side, it's immediately obvious that all connected higher point functions vanish because we have a Gaussian theory and the density is linear in phi. And indeed, if you carefully compute this fermion loop, and after accounting for all symmetrizations, you will find that it vanishes. So already here in this kind of free example, we see that there's an advantage. But this bosonization approach kind of also helps you if you want to study deformations of this theory. So let's say I want to couple this theory to something. So for example, let's look at the so-called Schwinger model, which is a fermion, like one plus one dimensional quantum electrodynamics, a fermion coupled to a photon. So on the fermion side, this looks like an interaction, right? We have this interaction between the photon and the fermion, which is relevant. So the charge has mass dimension 1. And there's no small number. It seems naively that it might just be not a hard problem. Whereas on the boson side, the entire theory is Gaussian, right? So this is how the photon couples to the massless scalar. And you can, again, immediately solve it just by looking at it. We can go in a gauge where the photon eats up phi. And so we see that the mass of the photon is gapped and has a mass equal to the charge. And again, the fact that you could solve it on the fermion side comes from this cancellation of all these diagrams, but it's not immediately obvious that there is such a simplification in this formulation. So, okay, so not everything is as simple as one-dimensional relativistic fermions. In general, there aren't all these loop cancellations, but in higher dimensions, we'll see that there's still a kind of remnant of these cancellations in the form of approximate loop cancellations. And these approximate cancellations make kind of perturbative analyses of Fermi liquids and non-Fermi liquids very difficult. It's even hard to know, if you look at a density endpoint function, how it's going to scale with momentum, because there's a kind of naive scaling, but there's a certain number of cancellations, and the ultimate scaling is going to be very different than what you expect. On the other hand, these cancellations are completely transparent in the bosonic description. So the same way that in the example we had before of a 1D relativistic fermion, these loops vanished because the boson side was free. In general, we'll see that the small remainder that, in general, we'll see that fermion loops don't vanish, but the small remainder, there's some kind of partial cancellations, and the small remainder post-cancellation comes from weak interactions on the boson side. So the bosonic description will have weak irrelevant interactions which control nonlinear response and higher point functions of densities and currents. And broadly speaking, there's going to be two sources of nonlinearities in the bosonic description. One is kind of coming from things like the dispersion relation of the fermion, and this even happens in one dimension. So I gave the example of a Dirac fermion, but if you have a different dispersion relation, that leads to some interactions on the boson side. But another source is kind of much more universal and inevitable, and just comes from the geometry of the Fermi surface, and in particular, the curvature of the Fermi surface will lead to interactions, nonlinearities in the bosonic description that are, completely fixed by geometry and you can't get rid of. So, the point of our work is to kind of to reveal these these nonlinearities. Okay, yeah. Any questions about bosonization, the general idea? Okay, so maybe I'll move on to the action. So our strategy again is to directly get an action for the shape of the Fermi surface. So that the Fermi surface is some object in momentum space, and it can wobble around, and you can parameterize it by some distribution function, but it's not just any arbitrary function. It's going to be a function that's only equal to 1 or 0. So 1 when states are occupied and 0 elsewhere. So basically, our degree of freedom is going to be a subclass of functions of x and p that satisfies this this condition that is equal to 1 or 0. Or you could say it more concisely that x squared is always equal to f. And we'd like to write down an effective action for this degree of freedom. So let's start with a case of free fermions, and we'll generalize later to interacting Fermi liquids. For free fermions, we already know what the equation of motion of this distribution function should be. It should just be the collisionless Boltzmann equation, right? So if I have some dispersion relation, and here I can even consider the case where I put my system in some external potential, then I know that the equation of motion for the distribution function is just this equation, the collisionless Boltzmann equation. So the name of the game in this case of free fermions is just to come up with an action that has this as its equation of motion. So that's our first goal. So let's think a little more about what our degree of freedom is. I said it wasn't just an arbitrary function of x and p. It's going to be a kind of subclass of these functions. So let's think of how we can span that class of functions. So let's start with a kind of seed state. Let's say a Fermi surface at rest. So here this is just a step function that's equal to 1 here and 0 elsewhere. So we start with a spherical Fermi surface, and let's try to think of what distribution functions f we can get to by kind of time evolution with some Hamiltonian. So let me write the equation of motion in this way that makes it look a bit like a Schrödinger equation. Here the commutator is just a Poisson bracket of these two functions. So this is what the equation of motion looks like. And I can formally solve it by exponentiating this commutator. Okay, and f0 is my kind of initial state. So here we see that the possible distribution functions that one can reach are basically the orbits of the seed state under some group G. And this is a group whose algebra, whose commutators are the Poisson brackets. So this group turns out to be the group of canonical transformations. The group of canonical transformations has an algebra, has a Lie algebra of Poisson brackets. So our degree of freedom is basically the orbit, and in fact, it's called the coadjoint orbit. If there are questions about why that name, I can explain. But basically, it's the orbit of this kind of seed state under the group of canonical transformations. That's where our degree of freedom lives. So we can parameterize it in terms of f, or we can parameterize it in terms of, say, a unitary that takes us from some reference state to f. Okay. And this unitary, we can also write it as e to the phi, where phi here, I'm using this notation kind of in analogy with Goldstone's, where phi is going to be like a fluctuation. So here u is an element of the group, so phi is an element of the algebra. This is the algebra of Poisson brackets. Okay, so elements of the algebra are functions of x and p. So that's what my degree of freedom is. Now notice that not every unitary u or not every phi is independent. Two unitaries that differ by one that commutes with f0 that doesn't modify the kind of initial state will lead to the same f. Okay, so basically my degree of freedom really lives in a quotient space of the group of canonical transformations divided by the group that stabilizes this this state. And so there's some kind of redundancy, and it turns out that you can use this redundancy to kind of gauge fix, reduce the number of degrees of freedom, and to make phi only depend on x and the angle of the Fermi surface rather than on the whole momentum p. So yeah, you can use this gauge redundancy to have phi depend only on x and theta. So at the end of the day, the degree of freedom is a scalar field that lives on the Fermi surface. For those that are familiar with bosonization, you'll recognize that this is also, it resembles a lot the degree of freedom they have there. So now we'd like to write down an action for this degree of freedom, either for phi or for f. And the idea is just to write down the most general thing possible in the mindset of effective field theory that's consistent with symmetries. So basically any functional of f. But there's one special term that you might not have guessed immediately. There's a Wess-Witten-like term, which even has a name. So it's a type of term that's always there for this type of quotient spaces for these co-adjoint orbits. It's linear and time derivative and has this form. It's very similar to the Berry phase term that you have in ferromagnets. In fact, there's a way of thinking of the ferromagnet case as a co-adjoint orbit where you have SU2 mod U1 and your kind of order parameter is, say, the magnetization. How should I write it? Let's say S spin equals M delta A Z. So this is kind of the analog of F0 for ferromagnets, and there's a special Wess-Witten-like term, a Berry phase term that's allowed by symmetries, which eventually leads to the Z equals 2, and so on in ferromagnets. So this is a very similar type of term. Rather than that, the idea is that we will add anything to the action that's allowed by symmetries. So any functional of f will be okay. The simplest that one could think of is just a linear functional of f. And here, just to give you some intuition, this should be pretty intuitive. I'm basically just integrating over f and weighing it by the energy of modes with momentum p. So this is what one would have to kind of leading order in f. And it turns out that this action, the sum of these two actions, the Wess-Witten term and this kind of Hamiltonian piece, have as equation of motion precisely the collisionless Boltzmann equation.
Luca?
So this is, yeah, question.
So G mod H is always symplectic?
For cojoint orbits, yes.
Okay.
Yeah.
Actually, can you give a little bit more intuition about what that WZW term is doing in terms of literally just the fermions? Is there a way to explain that?
In terms of the fermions, I think you can think of it, so right, in the cases where you have free fermions, you can probably construct this kind of semi-exactly, well, actually, in 1+1D, I guess, yeah, probably in 1+1D, there's some kind of exact constructions where there's like these coherent space constructions of these terms that are very similar to how you get the Berry phase term microscopically.
Oh.
That's probably, but let's see, to give some intuition.
Oh, it's fine. It's
so
a thing that is so obvious.
Yeah, it's not super obvious. It's really, here we have bosonic degrees of freedom, so it's not entirely obvious what this looks like in terms of fermions, but it's yeah. But in any case, this is an action. So one thing that's important is that it's not linear in F. So this, this term is linear in F, but this term is kind of highly nonlinear, right? F is and so it actually will lead to nonlinear response and all these things, and it actually will reproduce fermion loops and so this is a kind of bosonic theory of free fermions, of a free Fermi gas, and yeah, of bosonic observables in a free Fermi gas. Right, but here we don't have to stop at free fermions, and the kind of idea of effective field theory is to write anything that's allowed by symmetries. So we'll just have more and more nonlinear terms in terms of this distribution function f in a local way. So here all the f's are at the same coordinate. Of course, there can be higher gradient terms. I didn't write any, but you could have higher gradient terms. It has to be local because the idea is that we didn't integrate out any gapless degree of freedom. And the leading term, this leading nonlinear term, turns out to be precisely the Landau parameters of Fermi liquid theory. But here we see more generally that there's a kind of whole tower of generalizations to Landau parameters, either higher order in fluctuations or higher order in gradients, which are kind of properties, non-universal properties of a given Fermi liquid. And in principle, you could measure them in helium or right? So this is the kind of most general action. Here you see that it kind of, most terms only depend on F manifestly, except for this West-Zumino term, which it kind of looks like it references this seed state that I used to generate my orbit, whereas it should only depend on F, right? F is my degree of freedom. So it turns out that variations of this action only depend on F, even though it's not manifest in this way. So in particular, the equation of motion is just the kinetic equation, so it really only depends on F. Good, so this is the action. This is the kind of fully nonlinear action. You can, in principle, kind of expand it around any shape of a Fermi surface that you want. So, your F0 could be any shape that you might be interested in. And then you could look at fluctuations. So F is something like U inverse F0 U, which you can expand. So it's going to look like F0 plus, and U is e to the phi. So F0 plus F0 phi plus 1/2. And all these commutators are Poisson brackets of these fields. Okay, phi depends on x and theta. So you can expand your fields like this and study fluctuations around any shape that you might be interested in. So let's look at the special case of a kind of spherical Fermi surface and look at how study fluctuations around that. So if you do this, what you end up with at the kind of leading order in the fluctuations is just this Gaussian action for fluctuations. So what it looks like, and here I'm specializing to 2 spatial dimensions, but you can do this in any dimension. And what we have, so here, let me just draw it. So this is for the case of a spherical Fermi surface or a circular Fermi surface, and n hat is a unit vector in the direction normal to the Fermi surface. So what we have here is basically a bunch of decoupled chiral bosons that propagate in the direction perpendicular to the Fermi surface. Okay, and this is exactly the kind of action that people wrote down in the early days of multidimensional bosonization. So the idea is that kind of, we understand bosonization in 1D, and to kind of leading order bosonization of Fermi liquids in higher dimensions is just a bunch of decoupled chiral bosons on the Fermi surface. And so similarly, one can look at a density operator. So the same way that, in 1D bosonization, the density operator was the gradient of the scalar. Here one could study this. There's a similar density operator, which is the gradient of the scalar in the direction perpendicular to the Fermi surface. And the total density you'll have to sum over all angles. So with this Gaussian action, you can already compute linear response. You can compute things like the density 2-point function. And it's a free theory, so it's just a tree-level diagram. So this computation is supposed to be reproducing some fermion loop, right? What's interesting is that unlike in 1D, there's still going to be an integral here, even though it's a tree-level diagram, which is coming from this kind of sum over species, right? This integral over theta, this sum over the field phi at every theta. And so if you compare to the fermion calculation, so the fermion loop would have, an integral over d omega and d2p in 2 dimensions, which I can separate into a kind of radial integral and a angular integral. So here in this bosonic description, we got rid of 2 integrals, and there's only the theta integral left. So it's as if we had kind of integrated out from the start all these frequency and radial momentum integrals in all diagrams. But you're still left with these theta integrals. And these theta integrals are crucial because they're what will give you non-analytic response, even though you have tree-level diagrams. And particularly, you reproduce Landau damping in this way. So this is the 2-point function of a free Fermi gas, which has this Landau damping. So this is something you can already see in this kind of Gaussian, approach to. And you can get this same result if you compute the fermion loop, but the fermion loop is, of course, much harder to compute. But now with our full nonlinear theory, we can go beyond this, and we can look at nonlinear response. We can look at nonlinear corrections to these things. And so just to show you kind of what these look like, so there's going to be here I'm showing you the action to cubic order. So we already saw the quadratic terms. but they're cubic terms. So some of them come from the West-Luminoid term. These are completely fixed by the geometry of the Fermi surface, and basically are related to curvature. So here, coming from the change of this unit, this how the unit vector n hat of theta depends on theta, and in particular, they also couple different patches together. Okay, there's theta derivatives. They couple them in a kind of local way here. So there's some nonlinearities that are completely fixed by the geometry of the Fermi surface, and there's some that come that are less universal, that come from the dispersion relation, and something like this even arises in one dimension. But it's it's not as simple as in lower dimension. It's not in lower dimensions. Like you have a kind of mixing of these effects. There's the dispersion relation enters in several ways in these nonlinearities. So with this cubic action, you can compute things like the density 3-point function or higher point functions. And in the original, so on the fermion side, it's clear that there is a density 3-point function. You can compute this loop. It's actually a very difficult calculation, but there's no reason for it to vanish like in 1D. Whereas in the bosonic description, if we just had this Gaussian theory, it would have vanished, right? Because if this were the total theory, the connected higher point functions of the density in this theory would just be 0. So it's clear that this theory was missing something. And here, this is what it's missing, at least at cubic order. And so you can compute the density 3-point function in this theory. There's going to be 2 types of diagrams, one that comes from these cubic interactions, and one that comes from the fact that the density also has corrections. So it's no longer linear in the boson. And in the special case of free fermions, you can actually compute both sides and check that it matches. But actually, the hard part of this check is to do the computation on the fermion side. This is a very difficult calculation, and so there isn't really a closed form expression in the literature for it. We had to take some limits and check it in some limits. So that's for the 3-point function. You can also go beyond, and in particular, if you're just interested in the general scaling of n-point functions, that's very easy to get in this approach. So, and in particular, you can see how many kind of non-trivial cancellations there would have been if you had started from a fermion description. So naively, in a kind of fermionic, for like a free fermion, say, if you computed the density n-point function in a free Fermi gas, you would guess that it scales with momentum in this way. So here, let's say I have n densities. Here I'm scaling omega like q. So this is kind of what a naive scaling analysis would give you. For n equals 2, this scales like 1, which is the correct answer. So this whole thing scales like 1 if omega scales like q. But for n larger than 2, this actually is wrong. And in fact, all of these these n-point functions scale like 1, it turns out. So really what I mean by 1 is some scaling function of omega over q. And of course, there are many omegas and many q's. So it's some complicated scaling function that has many parameters, but it scales like 1 in terms of momentum. So so we see that there's one cancellation in the 3-point function, and there's more and more cancellations as you go to higher point functions. So this would be very hard to see in any different approach. So these are these nonlinearities are terms in the effective field theory that are irrelevant in the sense that their corrections to things like the 2-point function are small. So this answer for the 2-point function is correct, and it has small corrections that might come from these terms. But they're still crucial in that without them, you don't get nonlinear response. So there's some observables that are completely fixed by these irrelevant terms. So that's one reason to care about them in Fermi liquids. But one other reason to care about them is that it is for non-Fermi liquids. So when in studies of non-Fermi liquids, first of all, the scaling is different. So it's less obvious what is relevant and what is irrelevant. And in particular, if you've read any paper on non-Fermi liquids, they have extremely complicated diagrams involving fermion loops. And you have to deal with these cancellations. So this is basically an approach that tells you, what to replace fermion loops by, and how to evaluate them. So that's one of the kind of directions to go into. What happens if we take this kind of version of a Fermi liquid and couple it and try to get a non-Fermi liquid? So let's couple let's couple this Fermi liquid, and let's do it just in the Gaussian approximation first. So I'm going to take the quadratic action and couple it to a gapless boson. Okay, so here I have some gapless field that couples to the density. So this this operator here is just the density to leading order of my fermions. So in a fermionic description, this would look like, you know, I have a fermion with some dispersion relation, and then I couple it through a Yukawa term with to a boson. So and you know, this interaction would be relevant. So it would seem like there's no way to solve this theory. But in the bosonic description, it looks like an entirely Gaussian theory. Okay, similar to how we solved the Schwinger model before. So you can diagonalize it. You can compute anything you want. In particular, if you compute the 2-point function of the external, the additional scalar field phi, this is what you'll find. There's the density 2-point function that appears here, and at small frequency, you get the famous z equals 3 scaling of non-Fermi liquids. This is at frequencies much smaller than Q. And all this you see just at tree level. Okay, these non-analyticities are coming from integrals over species, the theta. Basically, it's the integral that we did before. So you see this. You can also compute the specific heat of this theory. So you can take this effective field theory and just study at finite temperature, compute thermodynamic observables, and this produces the T to the 2/3 specific heats of non-Fermi liquids, which is kind of neat because you might have thought that we don't have fermionic states. It's just a kind of theory of the bosonic sector, but it still has it still knows about it's still the specific heat tells you about the density of states, but we're still kind of capturing the correct specific heat. So
Are you question? So this Z equals 3 result you're quoting from those papers. So you're saying those are not corrected by including nonlinearities or like the curvature effect. So when those papers were written, they were criticized for leaving out the curvature effects.
yes,
right?
exactly.
Because they couldn't handle curvature effects. So
Exactly.
and it was told, they were told that once you include the curvature effects that you don't know how to handle, this will be all evaporating. And you're saying they do not; that result does not evaporate. Am I hearing this right?
It might. Yeah, no, good. So that's right. So here I did kind of, I didn't do I was solving a kind of a toy model of the problem where I just kept the Gaussian part of the action. So these curvature effects, exactly, that's the point. That's where we can push beyond this work. So we know now how they look like, what these nonlinear terms are. I mentioned that they were irrelevant around the Fermi liquid fixed point, but now here the scaling is a little different. And it turns out that they're no longer all irrelevant. So there is room for Z not to be for a renormalization of this critical dimension. So this is something that we haven't done yet, but there seems to be room. So on the fermion side of things, in the fermionic approach to these non-Fermi liquids, there's an expectation that Z deviates from 3 at very high loop order. So I usually draw this diagram. Let me just show it to you to scare you.
Right, that's like Metzner kind of diagrams that most mortals cannot calculate.
Right, no one can, and in fact, even they can't.
So you don't know whether he's right because nobody else can do it.
That's right. Yeah, that's why it's hard to. But notice that even these people don't evaluate it. They just say there's some cancellation that happens in earlier in slightly simpler diagrams that made people think Z was exactly equal to 3, and what these people just argued is that this diagram seems there's no reason for these cancellations to happen in this diagram. So they don't actually compute the corrections to Z equals 3, but they just say, okay, it seems like there doesn't seem to be a deep theoretical reason for Z to be equal to 3. It seems like it shouldn't be protected, but it just happens at very high order. So two things. First of all, this diagram is a kind of instead of being for loop would be a 2-loop diagram in this bosonic approach because these fermion loops become vertices, right? And also, so it's the kind of thing that's much easier to actually evaluate in this approach. But also, you could just study being completely agnostic to whether or not Z has to be equal to 3. This theory with these nonlinearities that I talked about is a good different starting point for RG of Fermi surfaces. So that's kind of one of the directions that we're pursuing, doing RG with the nonlinear version of this action. And so we're hoping that it can address whether or not, then like either, I think the goal here would be either to find a deep theoretical reason that Z has to be equal to 3, or if not, compute the deviation and a little more explicitly in this simpler approach.
I have a very pedestrian question.
Yeah.
If I take small omega limit, do I not get a factor of I in it? Is that,
Yes, sorry, yeah, I should have written an I here.
I forgot if it was the conventional thing that there is an I, right? Or
Yes, there is an I. In real time, real frequencies, there's an I think. Okay, there might be an overall I, I'm not completely sure, but no, I think there should be an I. Good. So that's kind of the most of what I wanted to say. So there's a number of kind of extensions to here. I talked about the simplest case possible. I expanded around a spherical Fermi surface. I ignored spin. You can completely. It's entirely possible to include spin in these situations, and you'd have more degrees of freedom. So in the fermionic picture, you would have say fermions with spin, so I can represent them. I can represent fermion bilinears as something that lives in the adjoint, and so this is what my F would look like. So really, I guess phi. So phi basically lives in the adjoint in this situation with spin, and you have a bunch of degrees of freedom in this case that interact in some way. I didn't talk at all about BCS, but you can kind of recover known BCS physics in this approach. Fermi liquids are also special in that they have low energy kind of excitations at very large wave vector. So in what I described, I was kind of doing a gradient expansion, right? So I was looking at the low frequency and small wave vector limit. And that's, a limit where there's a lot of simplifications, but you can actually also capture large wave vector physics at low energies in a similar approach. Maybe I'll also make a comment, a connection to recent work by Elsenthal and Thorngren that suggested to kind of view Fermi liquids and maybe a class of non-Fermi liquids as systems that have an emergent symmetry, a so-called loop group symmetry, which roughly you can think of as a U1 symmetry at every point of the Fermi surface. And so because you have the symmetry, you have a current at every theta, so a current that depends on space-time and on theta, and that this symmetry has an anomaly, like a regular chiral for the anomaly, because there's now time, space, and this theta direction. And an extra ingredient is that the kind of background field for this emergent symmetry gets activated against your will. There's an emergent symmetry, you can't control background fields. And this is how it knows about the Fermi surface. So if you plug this in here, you can check that this equation has the right kind of Lorentz force. If you take a Fermi liquid and turn on an electric field, you deplete charges on one end and put them at the other end. What we see in our approach is that this anomaly equation is actually really only a kind of linearized approximation to a covariant conservation law for associated with the group of canonical transformations that I talked about. And basically, if you kind of linearize this equation, it looks like this, covariant piece in the conservation law looks a bit like looks like an anomaly term. So one kind of interesting thing in their work was to start to think about, okay, we have these systems that approximately have this anomaly, but are there things we can derive from the anomaly alone? Anomalies are powerful in that you can sometimes constrain dynamics from them without making any assumptions about the dynamics. You can prove the existence of massless degrees of freedom and so on. And so I think it would be really interesting to kind of consider more generally this nonlinear completion of it and see what follows from this. In a way, and this equation might transcend Fermi liquids. It might be valid also in a non-Fermi liquid state. In particular, it seems to, the same way that kind of the chiral anomaly in 1 + 1d tells you that you have a gapless degree of freedom, this anomaly basically implies a particle hole continuum. So it implies that you have a lot of gapless stuff. And I think it would be nice to kind of, that's one direction to explore it a little bit. And otherwise, the kind of general future directions that we're taking this in is Fermi surface plus X, meaning, we have this kind of nonlinear, this new approach to Fermi liquids. Let's couple it to stuff. So I talked about the critical boson, but you could couple it to phonons, to disorder, and all these things. And this might be a fruitful direction. But we're always looking for other ideas of what to do with this thing. So I'd be happy to chat if you have some ideas. So, okay, thanks a lot for your attention. That's all I wanted to say. Maybe I'll take questions now.
For the wonderful talk, and any questions?
Hey, Luca, it seems naively that H, your subgroup H, depends strongly on F0. Is that actually true? Like, does the coadjoint manifold depend on F0 in a strong way?
Not, well, yes, H would depend on F0, but the coadjoint orbit doesn't. So in the sense that if I start from another point, the H there is different, but it still has the same dimensionality and it would still generate that same orbit.
I see. What determines the dimensionality of H? Just the fact that you have a Fermi surface?
Right. Yeah, exactly. So the peculiarity of this function, okay, good. The fact that this is equal to 1 or 0. This alone kind of tells you, because basically, so you're looking for, when you look for H, let's talk at the level of the algebra. When you're looking for the algebra H, you're looking for functions of X and P that commute with F. So, and commute means in the sense of Poisson brackets.
Yeah, I think I understand.
Yeah, and then this guy. So here, let's consider a state that just depends on P, like a Fermi surface at rest. Okay, so this thing, I'll need a gradient of P acting on F, and this thing is only going to be activated at the Fermi surface, right? Everywhere else in the Fermi C it's 0, and outside the Fermi C it's 0. So alpha will only really have this thing. Alpha will only have a constraint at the Fermi surface. So yeah, you can see that kind of how many constraints there are on alpha for it to be in the stabilizer kind of only depends on the fact that the kind of codimension of the Fermi surface. So the size of this group is fixed by that.
I see, thanks. I have a follow-up question for that, which is, if I were to take the normal Boltzmann transport,
yeah,
and I were to expand it, but including higher order collisions,
yeah,
this is like basically a resummation of that series. Is that fair?
Yeah, I think that's correct. Like the equation of motion from our action was known. It's Fermi liquid theory. And so maybe let me go to my action. So the equation of motion that comes from this kind of general nonlinear thing is basically a kind of Boltzmann equation with a bunch of nonlinear terms in some way. And the first ones are just Landau parameters that you can see, that you can find that are typical first corrections to the collisionless limit.
But F3 is like some 3-body collision term, right?
That's right. Yeah.
But this approach is easier than doing that directly for some reason.
Yeah. So equation of motions are nice in some sense, but actions are a little more fundamental. It's easier to do RG with actions, and at the quantum level, we kind of believe, in quantum field theory, that actions have a little more information than equations of motion. But yeah, I think in practice, the idea is just that it's much easier to do RG with actions, to couple it to another degree of freedom, to make sure you know what you're doing with symmetries. It's easier to implement. I guess, yeah, there aren't, I guess that's.
I'd say, because one might believe that it becomes significantly different if, like, you were at finite temperature and then H changes because you have F that isn't just 0 or 1.
Yeah, so, okay.
This would be quite different, right?
Yeah, so our way of kind of addressing finite temperature is to not do that, because indeed that seems a little complicated. So yeah, what Yuri is asking is that, at finite temperature, obviously my f will be some kind of very different type of function. And what is the stabilizer of that? What is the cojoint orbit associated with this? That seems a little complicated. So our approach is rather to just derive the zero temperature action and then heat it up. So we end up with some effective field theory that has, the degree of freedom phi, and I can just do finite temperature physics with that. And, I'm always in a limit where T is much smaller than TF or, my chemical potential. Because once I hit these high temperatures, that's kind of the cutoff of my effective field theory. But so.
And that also presumably wouldn't look like the bosonic equation anymore because of the Western terms.
Right. Yeah. Right. Yeah.
I have a question.
Yeah.
So another, so bosonization is really nice for bosons, but fermions are harder to access, right? So I suppose you have the same issue, like you cannot get a single particle propagator for fermion and talk about the lifetime or I don't know, self-energy and those kind of things.
Right.
Because you're working with bosons.
Yeah, so yes, that's right. So yeah, we have some ideas to capture the fermions. I think so. In 1D, of course, there's these vertex.
Yeah.
But and some work on bosonization has kind of assumed that something like this happens in higher dimension, but that doesn't seem quite right, because there's a number of reasons. But phi is dimensionful. It has a stiffness. Yeah, it's a little. Doesn't seem like the right, and you can't just get fermions out of bosons without in higher dimensions without having some kind of, you need statistics to come out. But right, so I think, in a way, the fact that the fermion field isn't simply related to the boson field allows for a lot of possibilities. So you could, you could have a Fermi liquid with a kind of a single particle residue that goes to zero. And still have Fermi liquid response. If you said that the fermion was exactly tied to the boson, then somehow the quasi-particle residue should have been there somewhere, and that's not obvious where it is. So I think that maybe the fact that it's not so easy to build fermions is telling us something, that you can have Fermi liquids that have very different fermion response, single particle fermion. Right. That's one answer. We have some ideas for how to maybe incorporate fermions, but it's still very preliminary.
That would be miraculous. This is already really awesome.
Yeah, so a lot of like transports. There's still a lot of things you can talk about, connectivities, viscosities. Yeah. All these are bosonic things. Yeah.
Very good.
I have two questions. Actually, one is about considering Berry curvature inside the Fermi C. I guess you would have to include some extra term in it, or nothing changed.
Yes, good. Yeah. So let's see. Yeah, this can be incorporated. So you can kind of think of that Berry connection as a. Actually, let me first answer it in the context of this equation. I think they talk about it in this paper. So you can think of this Berry connection as one of the components of these gauge fields. Let's say the 3+1D case. You could even have, there you have two angles. Theta 1, theta 2, and you can have a Berry flux through your Fermi surface.
Sure.
So you can do the same for us. So this gauge field, you can think of it as kind of gauging our part of our big group, big symmetry group, and you can turn on a background field if you want. Yeah.
I see. Okay, and then you just have to modify the
yeah. So
convection somehow accordingly.
That's right. If you're studying fluctuations around this, yeah, you would. That's right. So it enters the action in some way, and it would affect equations of motion and so on.
Thank you. And the second question I have is that I guess you wrote here future directions is Fermi surface coupled to X. And there's one case which is extremely similar to just coupling to a boson, which is to couple to a gauge field. But there's a tricky business about finding the tangential component and the material component. And after some amount of argument, you get the same Z equals 3 dynamics for the gauge field.
Yeah.
Would you get exactly the same thing, or it's actually more complicated in here?
That's right. Yeah. So to leading order, I think you'll recover the fact that the electric mode gets screened and the magnetic mode gets Landau damped, and that and you can have a so like maybe let's say in 3+1D where there's less kind of non-Fermi liquid mysteries, you would have something like this, and in 2+1D you would potentially have a non-Fermi liquid because the magnetic mode is strongly coupled with the so you could do this I think at the quadratic level. So here roughly it's very similar to what I wrote here, right, with this phi. It's just that there's some kind of extra form, kind of form factor, let's say A of theta, in how it couples. And also like in the nematic case, you might want to put A of theta. So that's very easy to do here because we're really kind of keeping the whole Fermi surface. And so at the lead, I think at the kind of quadratic level, you'll already recover this fact that the kind of electric 2-point function is going to be screened. So there's going to be device screening. And then the magnetic will look something roughly like this. Yeah.
So
but
I guess,
then, yeah.
Sorry, I guess it's like, basically at this level, everything is kind of identical to the patch theory in some sense.
Is what's to the patch theory?
This is basically literally taking the patch theory and bosonize each mode inside the patch. I guess it's the same.
Yeah, that's right. Yeah, I think it's so. No, that's right. You kind of recover the patch theory, although the patch theory is always in the limits. You don't see this whole thing.
Right. Okay.
You're always in. I guess you're always in the omega much smaller than Q limit, which is nice for many things. But notice that often in transports, we're interested in the DC connectivity. Q is 0.
Yeah.
Or so the optical connectivity at Q equals 0. So sometimes you actually need both the kind of whole scaling function. That's one thing. Another thing is, I think in these, so patch theories have been used all over the place for everything in non-Fermi liquids. One thing that I think they kind of miss is this fact that there's kind of very rapid thermalization within patches. But if you look at the whole Fermi surface, there's kind of slower stuff happening, like these kind of slow wobbles of the Fermi surface that maybe happen at different time scales. And I think kind of keeping track of the whole Fermi surface might be important to really kind of have a comprehensive understanding of non-Fermi liquids.
Other questions? Okay, I guess if not, let's thank Luca again for the wonderful talk. That's it for today. Jonathan, if you're there, you can turn off the light screen.